So, in the last half we have seen definition and some examples of prime ideals and maximal ideals, and also we have a criterion how to test some ideal is maximal or prime, and they are just going modulo them and then the new ring whether it is an integral domain or not or is it a field. This thing will test us whether the ideal is prime or maximal. But now the original question what I was asking today, that whether is there a prime ideal at all or is there a maximal ideal at all, and that is answered by the following theorem. So, this is very important theorem, and as you will see the proof is very easy. This theorem is called Cruel's theorem. Cruel has proved this in the beginning of 20th century, that is 1930s. So, I will just here 1930s approximately. So, it says let A be a non-zero ring. Then SPM is non-empty. That means there is at least one maximal ideal there, and once there is one maximal ideal, this spectrum is a bigger set. So, if this is non-empty, if the subset is non-empty, then the bigger set is also non-empty. So, that answers our question, and this let us prove this proof. So, the proof uses what is called Zorn's lemma. I will state it, and as you might be aware that the Zorn's lemma one cannot prove it, we can only prove it, it is equivalent to what is known as axiom of choice. And I will not go into much of this because that is really a topic of set theory, and in mathematics Zorn's lemma is very well known and taken it that the statement is true, but true means what? It is equivalent to some other axiom of set theory. Okay, so, it is really an axiom, alright. So, what is that we want to prove? We want to prove that there are maximal elements where we are considering this order set, this partially ordered set. Consider the partially ordered set which set IA ideals in A and remove this unit ideal, and this is ordered by a natural inclusion. So, you see A contained in the ideal B, this is a relation on this set, and it satisfies which properties? I am just recalling what is the partially ordered set. It should be reflexive, it should be transitive, right. So, and it should also be, it is also antisymmetric in this. So, because A is contained in A, if A is contained in B, B is contained in A, then A equal to B, and if A is contained in B, B is contained in C, then A is contained in C. So, this is reflexive, antisymmetric, and transitive. Actually, if this I just wanted to make this comment also sometime, that this is, if you see older books, this word is not there, it is an ordered set. So, an ordered set is a set X with a relation on that which is denoted by this less equal to that relation should satisfy these three properties. Then you call it an ordered set. But somehow in the literature this is called a partially ordered set, maybe mainly because of computer science people. Okay, so all right. So what is we want to prove? What we are considering this ordered set, and what is to be proved? We want to prove this set, this partially ordered set has maximal elements. That maximal element will give you the maximal ideal, that is by definition of a maximal ideal. And as you see, there could be many more maximal ideals in a partially ordered set, because it may not be it's not totally ordered. So any two elements are not comparable. So once you start doing some chain will end here and some chain will end somewhere else. So these two definitely both of them will be maximal element, but they may not be equal. So there may be many maximal elements. So I just note here many may not be unique. All right. So we need a statement. How do you test a given partially ordered set has a maximal element? What condition do you need to prove? So that is precisely answered by John's lemma. So that let me state that John's lemma now. So this is John's lemma. Let I will write here x less equal to be a partially ordered set I would like not to write like this, but just in order not to get confused with the later books, I am writing it. If or suppose that every non-empty chain in X has an upper bound, then X has maximal elements. This is everything with respect to this relation. So let me explain what are the terms in this statement. So the first one is chain in X. So what is a chain in X? So I am writing it here. Chain in X means a totally ordered subset of X is called a chain. That is a chain. That means Y is a subset of X and any two elements of Y and Y prime, they are comparable, either this or Y prime is less equal to this. So given Y and Y prime in Y, we have either this or this. That means you can compare them with respect to this given order. That is a chain. And what is an upper bound for a subset? An upper bound for a subset, upper bound for any subset Y of X, this is an element X in X such that Y is less equal to X for every y in y, and this x may belong to y or may not belong to y. So, strictly speaking, one should write here upper bound in x, let us just to be precise. So, that explains this term upper bound, and x as a maximal elements is also clear. Both this whole statement, from here to here, that every non-empty chain has an upper bound in x, this is also abbreviated as partially ordered set, which is inductively ordered. That is the meaning of this is this sentence. Every chain in x has an upper bound in x. All right. So, let us come back to our proof of Zorn's lemma. No, not Zorn's lemma, sorry, theorem of Krull. So, what do we want to prove? We want to prove, so already we have noted that, so okay, it does not allow me to go. Okay, so proof of Krull's theorem. We are considering IA minus this unit ideal. This is partially ordered set, we already noted. All right, and we definitely know this is non-empty. This set is non-empty. IA minus this A is a non-empty set, because 0 belongs there, 0 belongs to IA and 0 is not A. This is the condition, because 1 is here and 1 cannot be 0. So, this is equivalent to saying the ring is non-zero. This says it is non-zero. I do not have to write this part. That is given to us. So, therefore, given assumption says that this is a non-empty set. Now, I want to conclude that this set has a maximal elements. So, I have to prove this set is inductively ordered. That means, if I take any chain in X, it should have an upper bound in X. All right. So, since SPM of A is by definition max IA minus unit ideal this way to inclusion, this is the set of maximal elements. Enough to prove that this set IA minus this with respect to this is inductively ordered. For this, let C contained in this be a chain in this set. That means, it is a subset and it is totally ordered. Which has an upper bound also we are assuming. Okay. So, what is this C? C is some set of ideals. C is a set of ideals, non-unit ideals, and we want to produce a upper bound for this. So, let us consider union C, this is the ideal C in the chain in this subset C. this is, I am considering this union. This is a union which is contained in the ring A, and I want to claim that this is the upper bound for C. So, we shall prove that, let us give some name to this. So, let us call this as A. A is an upper bound for this, for C, for C in this, and then we are done. If you prove this, we are done. Okay, so it is clearly an upper bound because this A, this subset A is bigger than every C in ideal. So, since A contains every ideal C, the real problem to prove that it is actually an ideal. So, enough to prove that A is an ideal in A, and A should not be this. A is not equal to A, it is a proper ideal. Then it will be an element here, and therefore we will be done. Alright, so let us prove this A is an ideal. So, what do we have to prove? That means you have to prove that it is a subgroup and it is closed under arbitrary scalar multiplication by of a capital A. Okay. That is where we will use the fact that this C is totally ordered. Okay, so take any element in the union. A is in the union, A and B both are in this A, that means this A and B are in the union. So, therefore, this A will belong to one of them, B will also belong to one of them. So, suppose A belongs to some C and B belong to some C, not this C. A belong to some C, this is a Gothic C and this is a script C, and B belong to some C prime. But then the C and C prime, C prime, they are elements in the chain. So, because of the total order we may assume C is contained in C prime. Then A is there and B will also be there. Then A and B both will belong to the C prime, but C prime is an ideal. So, that will check that, so that will imply that A minus B will belong to C prime, and C prime is contained in this A. Therefore, this is a group, abelian group, and now we have to check that arbitrary, but that is same. So, similarly, C times A belongs to the ideal A for every A in this A and C is in the ring A. Same thing again, look at A, and A will belong to some ideal C and this C is in A. So, and C times A will belong to then that particular C because that is an ideal, and therefore, this is more easier than the plus minus. This is, we should write this. So, what did we check? We checked that this union is an ideal. Now, we have to check it is a proper ideal, but that is also very simple. If it is not a proper ideal, if A is equal to capital A, then what will happen? One will belong to the union, one belongs to A, that is the union C in C, therefore, one belongs to one of them. So, 1 will belong to one C for some C in C, but this was a subset of I A minus A. So, if 1 belong here, but that is equivalent to saying C will be the ideal A, and that is not, it is not possible because this is contained, not possible. So, that proves that this A is a proper ideal, and therefore, we have proved therefore every chain has an upper bound, and therefore, conclusion this subset, this set is partially ordered set has maximal elements. Which are precisely the maximal ideals. So, that proves that given any non-zero ring, it has some maximal ideals. So, sometimes it may be unique, only one, sometimes it may be finitely many, sometimes it can be infinitely many, and so on. Okay, one corollary we can mention, whatever we did above, that we can do it little bit finer. So, let A be a ring, and A, ideal A, which is a proper ideal. Then there exists a maximal ideal M in A. So, that is M belong to SPM A such that A given ideal A, this is a proper ideal contained in M. Proof. Now, what do you consider? Again we apply the Zorn's lemma, or you can apply the above theorem to the ring A modulo this A, and because A is a proper ideal, this ring is non-zero. So, we can apply, and we can take a maximal ideal here. So, there is a maximal ideal here, but that maximal ideal will come from the maximal ideal of A. You do either this, or when you consider that this set, we have considered this set in the Zorn's lemma now. Here in above theorem we have considered this set, this partially ordered set, and then proved that this has maximal ideal. Now, instead of this you can consider not all ideals, but ideals B such that first of all B is a proper ideal, B is not A, and A is contained in B. So, consider this set and then apply the similar thing. That means, it will have maximal element that will obviously contain A by definition. So, more than this we will also prove a little bit better connection. The same thing again we will prove later with better notation. But also one more corollary I want to note. Corollary 2, let A be a ring and an element A in A which is not a unit, that is this A is not in A cross, this is a set of all units. See, you should use the notation again more often so that you will get used to the definition. This is A units. All right, proof. Let A be the ideal generated by this small a. Then because A is not a unit, this ideal is proper ideal, and then apply earlier corollary. I have not completed the statements. Then there exists a maximal ideal in A with A belonging to M. Then apply earlier corollary to the ideal A, which is the principal ideal. So, this is also handy sometimes, because when you want to prove some element in a given ring is a unit, then you should prove that this A does not belong to any maximal ideal. Okay. All right. Now, so for some more examples, I need a concept of modules and algebras. So, I think I will start today slowly. So, I will write here modules and algebras. So, this will give us more algebras are very important. You have studied probably in linear algebra, one fixed algebra studied there, and it is very important to be very precise. So, all right. So, let us recall, a module is an analog. So, module, this word is an analog for a vector space. So, like for a vector space you need a base field. So, this is usually written as vector space over a field K. So, what is it, recall in a minute? So, usually the notation used for vector space is V. So, what is a vector space over a field? So, field is given to you. So, vector space is an abelian group V plus. This is an abelian group together with a scalar multiplication. And what is the scalar multiplication? Scalar multiplication is a map from A cross V to V, and this map, the image of pairs A comma V is denoted by A times V. That is just so this is this A is K. So, that is a scalar multiplication. Scalar multiplication, one should think a map from K cross V to V. If you have a pair of an element in a K and V an element in V, then their image is written as this, and this scalar multiplication and this abelian group addition, that should be compatible with each other. So, there are obvious conditions such that, so since there is no place here, I have to go to the next page. So, what does it satisfy? It is very important to these I will call it a compatibility conditions. Compatibility conditions between the abelian group plus and scalar multiplication. This K cross V to V. So, what are that? Now, here one has to be little careful because there is a plus in k also, and we are denoting by the same symbol. So, it should be clear from the way of writing. So, scalars are usually denoted by ABC, vectors elements of V are denoted by V, W, etc. So, if I have two elements V and W, then what can I do? I can add 2 in V and W in V and then multiply by A. Multiply by A means scalar multiply, the scalar multiply. So, but on the other hand, I can scalar multiply A by V, V by A and V by W, A by, so not V by W, A by W, A W and add them in V, this should be same result. Similarly, if you have two scalars A and B and I can add scalars in the field and multiply by this V, multiply means scalar multiply, this should be same as AV plus BV. This addition is obviously in V, this addition is in K. Similarly, for the multiplication in K, so that is A P, this is multiplied in K and now scalar multiplication, this should be equal to BV and then A, and then obviously one of them is 1 time 1 multiplied by V is V, and these are true for all V W in V, all A B in K. Then you call it a vector space over the field K. Now, in this definition, if I remove the fact that this K is a field, then and also demand these compatibility conditions, then I will have an abelian group. So, now K may not be a field. So, K is drop the assumption that K is a field. That means what? That means we are considering a commutative ring. And I will use the same notation V and an abelian group V plus with scalar multiplication from A cross V to V, again denoted by same, everything same, satisfying above compatibility conditions is called an A module. So, such a thing is called, then V is called an A module. Now, one might ask, what is the difference? Then why do you need to study modules? You already studied vector spaces. But there is a big difference, because when you drop this assumption that K is a field, then you have a ring which is not a field, then it may not have every element, every non-zero element may not be notable, and that will not give us the same results. In fact, one has to be little more careful with this. For example, no. So, let us see, I just want to see some example. See, remember in a linear algebra, first theorem one proves is every vector space has a basis. Basis means a linearly independent subset which is also generating set. I will repeat this definition, but just to show you that there is a big difference. To study modules is much more difficult than studying vector spaces, because the very basic result that every vector space has a basis will fail in case of modules. So, for that I want to give example. So, now let us take even the ring A equal to Z. Now, you see the only units in this are plus minus 1, and let us take the abelian group, let us say Z mod n plus dot modulo n. So, this is an abelian group, this is a finite group, and this clearly has a scalar multiplication of Z. So, what is the scalar multiplication? We need such a map, but you have integer a and residue class r bar. Then where do you map it? You multiply as usual AR and take the bar of that. Taking bar means divide by n and taking a residue. So, this is clearly compatible with this, so natural. This is a natural map and it is compatible. Therefore, with this Z mod n is a Z module. But in this Z module, every element is linearly dependent over Z. What should I produce for this? That means what am I checking? If I take any element here r bar, this if I multiply by suitable A, it should become 0. So, this is a dependence relation, it will become if A is non-zero. For instance, you can take A equal to n, then n times r bar is by definition n r bar, but which is already divisible by n. So, the remainder is 0. So, therefore, what we checked in this example is every element is linearly independent. So, leave alone, you cannot find any linearly independent subset in this. So, there will not be any basis, and once there is no basis, many things will fail. Study of linear maps will become more complicated. So, therefore, I will just mention here modules, study of modules, over commutative rings is much more difficult than the study of vector spaces over a field. This is certain, and as time goes on, I will tell you the examples which will not which will differ from examples over a vector, examples of vector spaces. So, we have to study this. So, these modules will also be very important in the study of commutative algebra, and they are also used in while studying the geometry. So, this algebra setup is big for the studying algebraic geometry. That is one of the reason why these algebraic geometry type courses are not offered in undergraduate level. Okay, so, with this I will stop this lecture and we will continue in the next lecture. Thank you.